This is the second part about relations. We already covered the part about the definition of a relation between two sets, and now we'll speak about the domain and range of a relation. The domain of the relation R from a set A to a set B is defined to be the set dom R. Dom for domain on R is the symbol of my relation, is defined as taking all elements X in my set A such that they can find Y in the set B where X is related to Y. While the range of the relation R from a set A to a set B is the set range. This RNG is just a notation for the range, and R is a symbol for my relation. You take all elements Y in B such that you can find an element X in the set A such that X is related to Y. We know that all the elements in a relation R, all elements are in the form of AB ordered pairs, where A belongs to the set A and B belongs to the set B. To find the domain, we collect all the elements which appears as the first coordinates in all pairs in the relation R, while to find the range, you collect all the elements which appears as the second coordinates in every pair in the relation R. Note that by definition, the domain of the relation R is a subset of A, while the range of the relation R is a subset of B. Let us stress this in an example. So we have here my set A contains 4 elements, minus 1, 2, 3, and 4, and the set B contains 5 elements, 1, 2, 4, 5, and 6. I define a relation denoted also by R in this example, which contains these ordered pairs of elements. You have minus 1, 5, 2 and 4, 2 and 1, and 4 and 2. So, what will be the domain here? The domain of R is just I'm collecting all the elements appears on the first entry of these pairs. So we have minus 1, 2, 2 twice, which in the set will be only 2, and 4, and so the domain is minus 1, 2, and 4. And the range of R, it is the second entry, so here we have 5, 4, 1, and 2. And this gives me the range of my relation. This example is an example where we have my sets are finite and the relation is finite, so I can list all the elements of the domain and the range easily from the definition. Note that since the relation is from finite set to finite set, we can represent it by using a row diagram. The set of elements where the arrow goes out will be my domain. So my domain here is minus 1, 2, and 4. While the set of elements where the arrow goes to will be my range. So my range is 1, 2, 4, and 5. Next, we look for a general example for any set A. We have the domain of the identity relation on A is the set A itself, and the range of the identity relation on A is the set A itself. To prove this, we note that the identity relation on A is from A to A, so the domain of the identity relation is a subset of A. And also the range of the identity relation is a subset of the set A itself. This is given, so to prove this one, we need the other way. We need to prove that A is a subset of the domain of the identity relation, and it is a subset of the range. Yeah, so if we assume A is an element in A, Then by definition of the identity relation, we have A and A in the identity relation. Since A appears as the first coordinates in some pair in the relation, that means A in the domain, and also A appears as the second coordinates of the relation, that means A belongs to the range. That means what? That means since A belongs to A, it means that A is a subset of the domain of the identity relation, and also A is a subset of the range of the identity relation. So this gives us that the domain of the identity relation is equal to A, and the range of the identity relation is equal also to A. Next, we look at an example of infinite set, and here I will take the set of real numbers. I define my relation R1 to be the set of all pairs A, B, such that the first coordinate is less than the second coordinate. So in this example, we want to show that the domain of my relation R1 is a set of all real numbers, and the range of this relation R1 is a set of all real numbers. So what it means that the domain of my relation R1 is a set of all real numbers. It means that if I take any real number A, I can find another real number B greater than A. So the pairs A, B will belong to the relation R1. This means that for any A real number, we have to find B a real number such that A is less than B. If this is true, that means this pairs AB belongs to my relation R1, and that means the domain of R1 is all the set R. Similarly, the range of my relation R1 is a set of all real numbers. It means what? It means that for any element B real number, we can find a real number A such that A is less than B. If this is true, that means the range is that means AB in R, and that means B belongs to the range. Now we understand better the statement of the example. Let's look to the solution. So we want to prove again that this domain of R1 is the set of all real numbers. So by definition, we have the domain of my relation is a subset of the real numbers because the relation is from R to R. So this direction comes for free by definition. Now, what we want to prove, we need only to prove that the set of the real numbers is a subset of the domain of R1. So I assume that A is a real number, and then I need to find some pairs where A is the first entry, and simply I choose that A is always less than A plus 1. So this A and A plus 1 will be in my relation R1, and that means what? That means this entry A in the domain of R1. And I just prove that R is a subset of the domain because we take any element in a real number, and we found that this element is in the domain. And so from this one and this one, we have our first identity that the domain of this relation is a set of all real numbers. Similarly, to prove that the range of my relation is a set of all real numbers, because the relation is from R to R, so by definition the range of this relation is a subset of the set of real numbers. So I will assume that B is a real number, and so I have to find an element which is less than B, and I choose B minus 1. We know that B minus 1 will always be less than B, and so B minus 1 and B belongs to my relation R1, and that means what? That means because B here is the second entry, that means B is in the range, and so the set of real numbers is a subset of the range. And so I get my second equality, that the range of my relation R1 equals the set of all real numbers. And this ends the proof. Now let's look to another example. This time I will take a relation R2, and it is also from R to R, and this relation R2 is defined by taking all pairs X and Y such that the first square plus the 4 times the second square is less than equal to 16. So we want to find the domain of this relation. So the idea here is to take any element X in the domain and try to find some relation which defines the elements in the domain. So I will take X in the domain of my relation R2. And what it means that it is in the domain. By definition, it is in the domain. That means we can find a real number Y such that this X plus 4x squared plus 4y squared is less than or equal to 16. But this identity here, it means that x squared is less than or equal to 16. This inequality because x squared is less than or equal to x squared plus 4y squared, and this one is less than or equal to 16, and the square is less than or equal to 16. That means x is in the interval from -4 to 2. And therefore, any element in the domain of my relation R2 is in the interval from -4 to 4. Now the question is any element in the interval is also an element in the domain of R2? So we take an element A in the range from -4 to 4. And we notice that if I take any element in this range, then A squared will be less than or equal to 16. And so A squared plus 0 is less than or equal to 16. And that means what? It means that A is related to 0 under this relation R2. And that means A in the domain of R2. So I take any element in this interval from -4 to 4. I find this element in the domain of R2. And that means what? It means that from this inclusion and this inclusion, that means the domain of R2 is the interval from -4 to 4. Let's look to another example. Here we take the same relation R2 from R to R, given by all the pairs X and Y, such that the first X squared plus fourth the second Y squared is less than or equal to 16. And this time we want to find the range of this relation R2. We see that the solution will be similar to the previous slide. So, to find the range, the idea is to take an element in the range and try to find some identities or relations define the elements in the range. Now, if we take Y in the range, by definition that means we can find a real number X such that x squared plus 4y squared is less than or equal to 16. But here this one is squared plus this one is squared. It means that 4y squared is less than or equal to 16. It implies that y is in the interval from -2 to 2. That means what? If you take any element in the range, then you find this element is in the interval from -2 to 2. And then the question is the other inclusion also satisfied? If I take an element in this interval, it will be this element will be in the range of this relation or not. To answer this question, I will take an element B in the interval from -2 to 2. I will notice that this element for B squared, because it is in this interval, so 4B squared will be less than or equal to 16, and so I can add 0. That means 0 is related under R2 to my element B, and that means B is in the range of my relation R2. Hence, the interval is a subset of the range of my relation. And so we can conclude that the range of my relation R2 is the interval from -2 to 2. So in previous video we spoke about the definition of a relation, and this video we spoke about the domain and range of a relation. And in next videos we will speak about the inverse of a relation and what we mean by the composition of relations.